Hey everyone. This video is over activity 9.2 where we're sticking with the same gender and drug example, and now we're working with a different population of elderly people. Okay. So in this data file, gender is coded so that 1 is male and 2 is female. So if you click on gender there, I can change the value label. 1, I'm going to change it to male, and 2, change it to female. That way our output will be labeled with male and female rather than 1s and 2s. I'm also going to change the drug from 1 and 2 to A and B, again, just so things are labeled better than just with 1s and 2s. All right, so what we're going to do now is run an ANOVA. So click on ANOVA menu and then the analysis of variance, ANOVA here. Okay. And gender is our first factor, drug is our second factor, and we're looking at the impact of gender and drug on memory scores. So that's our dependent measure. Okay. And as we do that, you see that you end up with your ANOVA summary table off to the right, but you'll notice that it doesn't give you effect sizes, right? It doesn't give you omega squared or partial eta squared. To get those, you click on additional options and ask for estimates of effect size. I'm going to get omega squared and partial eta squared, but not eta squared. And while you're down here, you might as well ask for descriptive statistics as well. Okay. So what we're going to look at is we're testing 3 effects. We want to know if there's an interaction between gender and drug. We want to know if there is a main effect of gender and if there's a main effect of drug. So we're going to start with the gender by drug interaction. Okay, so the gender by drug interaction is where we're going to start looking at this third line in the ANOVA summary table. Okay, so we're looking here at an F for gender by drug of 4.74. And that F has 1 and 116 degrees of freedom. So the second degree of freedom is always the residual degree of freedom. Okay. The P is 0.03, which tells us that it seems like we have a real interaction there, that the interaction we're observing is unlikely to be due to sampling error. So to get a good feel for this, we're going to look at the graphs. So if you click on descriptive plots, and I'm going to make drug, put it on the horizontal axis and make separate lines for gender, but you could flip-flop those if it would make more sense for you. I'm also going to put in error bars with confidence intervals. All right, so if we look here, we can see that for females, they seem to do just a tiny bit better with drug A than drug B, but males seem to do quite a bit better with drug A than drug B. Right? So the definition of an interaction is that the effect of one variable depends on what level of the other independent variable you're talking about. So the effect of drug A versus B depends on whether you're male or female. Right? And so you can see that there's a difference here. For females, they're about the same no matter which drug they took. But for males, they did better with drug A than drug B. Right? But all the p-value for that interaction tells us is that at least one of those differences is different than the other one. Right? So in order to investigate this more carefully, we're going to look at the simple effects. So to get the simple effects, we are scrolling down to the simple effects menu, simple main effects menu. And I'm going to use drug as my simple effect factor, and my moderator factor is going to be gender. Right? So what we're doing here is computing an F for males with a p-value. So what this is doing for males is comparing these two means for males. So for males with drug A, their mean memory score was 21.06, and with drug B, it was 17.42. Right? So our P is 0.0003, which shows that that difference is really unlikely to be due to sampling error. Okay? Very unlikely to be due to sampling error. Now you could also compute the size of the effect by taking the difference between these two means and dividing it by the average of these two standard deviations. I'm not going to do that right now. I'll leave that for you guys to do. You can get an effect size D by just taking the mean difference divided by the standard deviation average there. Okay, but overall, it looks like a fairly sizable difference, right? It's a difference of almost 4 there between drug A and drug B for males. For females, we're looking at a difference between 20.68 and 20.05, which is a really small difference. And the F there is 0.42 for females with a P of 0.52, which means that for females, that difference we're observing is probably just due to sampling error. And you can just look at it and see that it's small and probably due to sampling error, right, when you're looking at these two numbers in the graph. But you still need to look at the p-value. You can't just look, right? Look at the p-value to be careful there. All right, so we have an interaction. Something different happened for males and females. Males did better with drug A. Females, it didn't really matter which drug they took. Okay. All right. So note that you do get an overall effect size, omega squared, for the interaction, 0.03 or 0.027, which isn't as informative as looking at the D's, or the effect sizes for the simple effects, right? You want to know how big was that difference for males and how big was that difference for females. And you're going to compute D's to do that. And again, to compute those, you can just take the average, the difference between the means divided by the average of the standard deviations for males and then also for females. Okay. All right, so we have an interaction. Now we also want to look at the main effects. Okay. So let's start by looking at the main effect of gender. Right, the main effect of gender, the F is 2.65 with 1 in 116 degrees of freedom. The P is 0.106, right? And so that p-value is, there's about a 10% chance that I would get an F of 2.65 or bigger if the null is true. It's kind of marginal, right? Sort of like we're not sure, right? Kind of withholding judgment, not 100% sure. There's some evidence for a gender effect. So if we look at these means, let's look at the marginal means for gender. So I want to know overall how high was memory scores for males and how high were they for females. So under the marginal means, under additional options, you just move gender over into this box. So my marginal means, I see that males on average had a score of 19.24, females had a score of 20.37, right? So that difference is, somewhat likely to be due to sampling error. I probably withhold judgment and not make firm conclusions about that right now. Okay. Also note that it's not that interesting, right? We're certainly trying to make a broad statement about males or females having higher or lower memory scores because we're manipulating drug A versus drug B. And so any difference we're observing might just be in part due to the difference between them and the drugs. Okay. Now we can also do the same, look at the main effect of drug, where my main effect of drug has an F of 9.56. So here we're comparing overall memory scores on drug A versus B. And here our P is 0.002. Right. Now if we look at the marginal means that were being compared there, for drug A, memory was about 20.87. For memory B, it was, for drug B, it was 18.73. So overall, people recalled more with drug A than drug B. But notice how misleading that statement is, right? So people did not. Males did better with drug A than with drug B. Females did about the same with drug A and drug B. So that interaction is what's really important. It's driving all of the results here. It's the most important finding, and it's the first thing you're going to talk about or the thing you're going to emphasize the most when you're discussing your results there. Okay. All right, so again, I have not given you every single thing that's in the activity, but this will walk you through at least how to get the analyses and the output in JASP and finding the numbers there that you can work with. Okay. All right, good luck on the activity.